at about 68 meters per second, which is roughly 150,000 miles per hour. In a universe where expansion usually pushes galaxies away from each other, this behavior is unusual. Most galaxies act like dots on the surface of an inflating balloon. When the balloon expands, every dot moves farther apart. That's how cosmic expansion works. Space itself stretches, carrying galaxies along with it. But Andromeda doesn't follow that rule. Instead of moving away, it's coming straight toward the Milky Way, almost as if it's on a direct path to collide with us. Scientists have known about this future collision for a long time, but the deeper reason behind Andromeda's motion has only recently become clearer. New research suggests that both the Milky Way and Andromeda are embedded in a vishale, flattened sheet of dark matter. Dark matter is invisible. It doesn't emit or reflect light, but it has gravity, and that gravity shapes the universe on the largest scales. Traditionally, scientists thought dark matter formed a roughly spherical halo around galaxies, but now it appears that, at least in our region of space, it may be spread out more like a giant pancake stretching across millions of light years. This shape makes a big difference. Gravity depends not just on how much mass there is, but also on how that mass is arranged. A sphere pulls evenly in all directions, but a flat sheet pulls more strongly along its plane, creating an uneven gravitational effect. To picture this, imagine a stretched rubber sheet. If you place a heavy object like a bowling ball on it, the sheet dips. Now roll a marble nearby, and it will curve toward the heavier object. In a similar way, the Milky Way and Andromeda sit on this enormous dark matter sheet, and its uneven pull guides their motion. Instead of drifting randomly, or simply pulling on each other, the galaxies are influenced by the larger structure they're part of. Andromeda isn't just heading toward us by chance, it's being directed along a kind of gravitational pathway shaped by dark matter. There's another important factor at play: cosmic voids. These are vast regions of space that contain very little matter. Because they have less gravity to slow them down, they expand faster than average. As they expand, they push matter toward their edges, forming dense regions filled with galaxies and dark matter. The Milky Way and Andromeda sit near one of these dense boundaries, sometimes called a cosmic wall. As the nearby void expands, it funnels matter into this region, strengthening the gravitational forces that influence the motion of galaxies. This means Andromeda's approach isn't just about the pull between two galaxies. It's the result of an entire cosmic environment shaping their paths. Even though Andromeda is moving incredibly fast, it's still about 2.5 million light years away. At its current speed, it will take around 4.5 billion years before it reaches the Milky Way. That might sound like a long time, but on cosmic timescales, it's relatively soon. In fact, Earth itself formed about 4.5 billion years ago, so the time between now and the collision is roughly equal to the entire history of our planet. When the two galaxies finally meet, it won't be a dramatic crash, like two solid objects colliding. Galaxies are mostly empty space, and the distances between stars are so vast that direct collisions between stars are extremely unlikely. Instead, gravity will reshape everything. As the galaxies pass through each other, their structures will stretch and distort. Long streams of stars, called tidal tails, will extend outward like glowing ribbons. Gas clouds will collide, triggering intense bursts of star formation that light up the surrounding darkness. Over billions of years, the two galaxies will gradually merge into a single, larger elliptical galaxy, often nicknamed Milkdromeda. This new galaxy will be rounder and more diffuse than either of its predecessors. What about our solar system? It's likely to survive the merger, but it won't remain unchanged. Our position within the galaxy could shift dramatically. We might move farther from the galactic center, or end up in a completely new orbit. The night sky would look entirely different. Andromeda, which currently appears as a faint smudge in the sky, will grow larger and brighter over time, until it dominates a huge portion of the sky. Familiar constellations will disappear as stars are rearranged into new patterns, creating a completely unfamiliar view of the cosmos. For many years, scientists believed that Andromeda's motion could be explained simply by the gravitational attraction between the two galaxies overcoming cosmic expansion at close distances. While that explanation works to a point, it doesn't fully explain why Andromeda is moving at its specific speed or following its exact path. The newer understanding shows that this motion is influenced by a much larger cosmic structure, including dark matter sheets and the effects of expanding voids. It's not just a two-galaxy interaction, it's a whole system shaping the outcome. Dark matter itself remains one of the biggest mysteries in physics. It doesn't emit light, so we can't see it directly, but we can detect its presence through its gravitational effects. For example, stars at the edges of galaxies move faster than they should if only visible matter were present, which suggests there's additional unseen mass. Scientists estimate that dark matter makes up about 85% of all matter in the universe, while the ordinary matter that makes up stars, planets, and everything we interact with accounts for only about 15%. Some new ideas even suggest that what we think is a supermassive black hole at the center of the Milky Way could instead be a dense concentration of dark matter made of extremely light particles. This model proposes a compact core surrounded by a fuzzy halo, which could produce the same gravitational effects as a black hole. In 2022, the Event Horizon Telescope captured an image showing a dark shadow surrounded by glowing gas at the center of our galaxy, which is widely interpreted as evidence of a black hole. However, some models suggest that a dense dark matter structure could create a very similar image, raising interesting questions about what we're actually seeing. Data from missions like Gaia, which tracks the motion of stars with incredible precision, has revealed patterns that some dark matter models can explain quite well. These include changes in how stars move at different distances from the galactic center. While this doesn't disprove the black hole theory, it shows that alternative explanations are worth considering. Future observations, especially those focusing on the behavior of light around these regions, may help scientists determine which model is correct. The idea that dark matter forms a vast, flattened structure around our local group of galaxies changes how we think about our place in the universe. Instead of existing in a simple, symmetrical halo, we may be part of a much larger, invisible framework that guides the motion of galaxies. Shape matters, because gravity follows the distribution of mass. This is why Andromeda isn't moving randomly. It's following a path shaped by the structure around it. Even as Andromeda moves closer, the universe continues to expand. Distant galaxies are still racing away from us, and over billions of years, they may become so far away that their light will no longer reach us. Future observers living in the merged galaxy might see a much emptier universe, with few or no other galaxies visible. And yet, there's an interesting twist. The same dark matter structures pulling Andromeda toward us are also responsible for holding galaxies together, allowing stars to form, and ultimately making life possible.